Okay, so it's time to start here the second part of this lecture. So we will continue in these cases with these small antennas. Let's see here, Khaled, do you have a question? You've raised your hand, I think. Khaled? Okay, maybe it's sitting up. If you have the question, just come back with the question. I don't hear you at the moment, so. Okay, so we will continue with these small antennas and see what kind of properties they have. So this is the cases when we shrink the size of our dipole, basically. So we can ask different type of questions here. And if we take a first one, we can ask what kind of radiation pattern they have. And a generic thing when we start to shrink the size of these antennas, so we make them much smaller than the wavelengths, like lambda over 5, lambda over something, you know, smaller number there. What's happening is that the radiation pattern really start to become as a dipole. If they are above a ground plane, it will be a monopole, so half a dipole. And the really option you can do with this is that you can combine what's called an electric dipole and magnetic dipole. And that's done sometimes. And that can actually double the directivity. So if you have a regular dipole, it's like 1.5 maximum directivity. If you combine electric and magnetic, you can actually go up to 3. So there are quite some attempts to do that. But it is a typical dipole pattern. So this like donut that you have. That's a typical pattern when something gets small. And if you start asking what the bandwidth is of this kind of structure. So in all cases that happens there is that actually the size of the structure limits the bandwidth. And we know pretty much how much it limits the bandwidth. So we can actually say what is this that you can get out from a certain size? What is the bandwidth I should expect to get out of it? So we know quite a lot about that. If you can match them to something like you see in your patch antenna, that first you should make it resonant, so approximately half a wavelength, you tune the length of it to make it resonant, and then you move the feed point to make it 50 ohm. And in general, when it comes to these kind of small antennas, it's hard to do it, but it can almost always be done. And what it requires is some good engineering in some ways, some good skills, how to actually make them closer to 50. And it's not something that in some ways the physics is really stopping us from. It's more that we haven't designed it in a good way. So by making clever design, we can in many cases make it very close to 50 ohm. It can of course be very, very hard to do it, but it is in general possible to do it, I would say. Efficiency in these cases, especially when you go to higher frequencies, is usually a big problem. And when you shrink something in general, the efficiency goes down. And how much it goes down depends on what material you are using and so on. At higher frequencies, it's a larger problem because in some ways the losses and the metals can get worse. So there is some kind of connection between these cases. Like surface roughness becomes more an issue when you go to very high frequencies than it is at low frequencies. Skin effects and so on comes in. So we start knowing quite a few things about them. And if we look, the basic knowledge we get out of this is in some ways go back to lecture, I think, 2 in these cases. So there we looked at our our dipole antenna, which is a resonance of half a wavelength. So this blue curve here, lambda is equal to 2L. And what's happened when we shrank the size of it, of the current, we got this more current that just looks like a triangular shape on it. It's losing this cosine type shape. And the Hertzian one and slightly smaller, we calculated here, and we find this radiation pattern here, which is this donut. So the directivity here, it's omnidirectional, so it doesn't depend on phi. It only depends on the theta angle out and its maximum radiation in the broadside radiation from it. The simulations that you have done yourself in FECO, and also I've shown you, show that the bandwidth is in some ways narrow in some ways. When you shrink them, you get more and more limited bandwidth. And the calculation of a half wavelength dipole or not half wavelengths, the shorter dipole showed here that the radiation resistance is really going down. And when it's short, you can see an example here. You can see it's a couple of ohms when you go down in size. Now we've shrank it quite a lot. So if you just take the dipole and you make it smaller, it's not resonant, the radiation resistance is low. So we have to do something better. We have to change the shape of it to improve these cases. That's what we have to do when we make something smaller here. We cannot just take the dipole and use it at a lower frequency. So if we look at the quantities we have for this, so this is a quick repetition here, we had this Q factor. So one way of quantifying the bandwidth for these ones is actually to talk about their Q factor. Sometimes the Q factor is a quality factor, but in general it's just the Q factor because it doesn't measure the quality of it. We want the Q factor to be as low as possible for these kind of antennas. In many cases it's too high. If you have a circuit, many times you want it to have it high. So it depends what it is. So it comes into that you have an impedance, for example, of your antenna. You have some resistive part here and you have some reactance coming up there. If you then match it at its resonance frequency, you get some perfect match that goes down here. And of course, the bandwidth will depend on where I put the threshold levels of this. And the Q factor is used to give them a common ground. It just talks about what is the generic type of bandwidth that I can get out of this. So the fractional bandwidth that we use is that, of course, that we normalize these ones with its center frequency. So we get the fractional bandwidth. And it's something that again then depends on these threshold levels that we have here. And in these cases, we could see that if we have a half power bandwidth here, we had 5%. If we have 1/3, we got 2%. If we do the same thing with the Q factor, we can say that for the single resonances, we can get out the fractional bandwidth from the performance we have on the matching and the Q factor. And the resonance that we had here before, that was a Q of 43. So in some ways, we just say what is the Q factor of these ones instead of saying specifically what is the bandwidth. Then there are tricks to make this wider. So you can actually do clever cases sometimes and make the bandwidth wider by making some double tuning of it. And that comes in more advanced types of designs where you can get a little bit more. But in general cases here, you just have this Q factor to say what kind of bandwidth you have out of the small antennas. So if we take that and we look at some small antennas, really antennas that have shrunk their size compared to, for example, this dipole. And the generic shape that we have seen before, and you have learned it, is that what you do in the first or simplest case is that you do this type of meander line. So you try to take the length you have of this wire, but you try to fit it in a smaller size. And then we can see how do they perform in some ways. So if we do that, you can see some extreme cases here. So you can see one here that looks a little bit like a dipole. You can hardly see it, but there's a lot of wires that goes forward and back inside of these ones. It's easier to see if you look at these ones here. You can really see the wire. So you can see that this has been shrank quite a lot in some ways. And if you look then at its resonance frequency, that is then down to this number of 0.4 in this case. And remember again that this wire here, if we take these ones, and I make this now lambda over 2, that is Ka, which is 1.5. So by doing all of this wiring in these ones, maybe the one we saw is the next one of this one actually. Take these ones away and we draw that one instead. So that is 0.3 in that case. So you can see it's shrank a factor of 5. And what we had to do there is to take the wire here, basically going around here. So the wire length now is more than half a wavelength that you can see from the picture because it comes a lot of coupling between this. But the basic idea is anyway this: you have a long wire dipole you would like to have, make it smaller by making it like this. You can really shrink it. So here you can see we made it in total size here a factor of 5 smaller when we compare it in a general setting. And we can see some cases we get out. If we do this in the general case, you pay an enormous price. So the radiation resistance in these cases went down to 3 ohms. So that's not good. That is a very, very low number. The efficiencies you can see shrank down a little bit here too. The Q factor starts to be very high, 167. And now if you think about the half power bandwidth, that's basically 2 divided by this one. So very, very narrow frequency band it's used to. But then we can see that other types of design can affect some of these properties. So for example, if we go out and look at this antenna instead, this one here, you can see it's a more complicated version than this one. And if you compare them, you can maybe recognize what's happening. That is that this one here is a version of the first one where you folded it into itself in some way. So it's a folded type of meander line, which I also shown you before. And the effect that can get out of this foldering is that suddenly we can start solving these things with, for example, the radiation resistance. So the matching of it is now basically 50 ohm. So that can get out some of these cases. Ka, of course, also got larger in these cases. So there's some trade-off of these things. But you can see we can start shrinking sizes that really sits in these situations. So we have some ways of, like, you know, making things smaller, physically smaller, still resonating at the same frequency. So if we make some observation of these ones, as I mentioned here, that R0 here is higher for the folded structure. That was this 51. So we really start foldering it, and here we're foldering it basically 2 times, or if you said 4 times, maybe the other one is 2 times. You can see by making this trick in some ways, we can push it up. And we can also see another thing, that is this Q factor that sits here is high if this Ka is small. So if we look at, for example, these ones here, we can really see that 0.3 in this Ka really pushing up the Q factor a lot. And then we can see that one of them actually performs a little bit worse than the other one, which is in some ways this one here. It is an exception that is actually, if you analyze it in detail, you can see it's even worse than the other one, because these have the same size, but the Q factor here is basically a factor of 2 higher. So it's not the optimal design in that case. And then if we want to see how they can actually behave, we can actually start trying to understand how they behave. And one thing that we will see, or I will convince you of, is that the scaling of this has to do with this size. So the K to the power of 3 times A to the power of 3 is some normalization factor that says how the Q behaves. So if I take and plot that number here, and I plot it to the different aspect ratios, so basically here is a thin dipole, and up here would be a structure that looks like this. So either the width is high or it's very long in the other direction. Then these antenna sits on these points. And what it can be shown here is actually that we have a performance of this that will follow a certain line. So we actually know from the beginning that if we do very good antennas here, they will actually follow a line that sits like this. That is actually given by basic physics of this. And in some ways, we cannot lower the Q below these lines. So we can make antennas that sits in this direction above these lines, but not down here. That is not possible. So if you would like to, in some ways, lower your Q for the same electrical size, it's impossible. Physics bans that. To do it, you would need to do something that goes around the physics that really sits in these cases. And then you can ask question, can you actually get a lot of antennas designed in these cases? Yes, you can. So the first cases here, you can see it was just normalized with the Ka. If we do the same and we keep the aspect ratios instead, so I say now I have an electrical size here between 0.2 up to, yeah, this is the half wavelengths dipole, half of that one's a quarter of a wavelength at 0.8. you can really see that these are a lot of these meander-line structures here, and they follow the same line that sits there. So we are pretty familiar in some ways what the prices are for this and how good we can make these antennas. And there are design rules for these antennas. So a little bit complicated in some ways because it says how is the length related to this parameter and so on, but we can get them out. So in some ways we know how to make these antennas in a very, very good way. And then to get the basic understanding of this, it goes back to something 70 years ago now, which is called some results by Xu, and the Xu bound in these cases that actually fundamentally says what is the price of shrinking your antenna. So if you have your antenna here, so you try to design it, you have to take everything that's included in the antenna, because everything will basically radiate from these ones, every radiating part. You put a big sphere around it, so the size of that one is, or the antenna is inside of this sphere, and then you say that this one have a radius here, and the radius is a, so the diameter is then 2a. And what Xu derived in these cases is that the Q factor of your antenna is always then greater than this number. So if you have a size of this Ka, think about your dipole is 1.5, and then that you say that I would make that 10 times smaller, you pay a factor that is 10 to the power of 3, which is 1000. So your bandwidth will go down then a factor of approximately 1000, which is quite a lot, which means that this price we pay when we make something very small, it also becomes very limited in bandwidth. What it means purely physical is that this Q factor measure how much energy is pumping around your structure. It's a reactive energy pumping like this. It doesn't just radiate out. And the smaller you make it in compared to the wavelengths, the field is more of this behavior. If you make it large, it's more like, behaving just radiating out. But this is a pumping field forward and back. And that pumping electric field or electromagnetic field will dominate everything that's happening with antenna. And that is the price we pay when we make it smaller. We get larger components for that. That's pumps forward and back. If we would like to, we can look at another quantity, which is the directivity related to this, and that follows the same type of behavior. So it's basically 1.5 divided by the previous one, and that's because it's a dipole that sits there. So for a typical radiator here, that is then 1.5 Ka to the power of 3. And if we look at some typical antennas, so many different type of antennas, here you can see some dipoles. Here you can see some meander lines and some other shape of these ones. You can all see that they are on this side of this line. And if you look at the D over Q, then you divide it with it, so they are on this side of it. So there have been a lot of checks of this and where the antennas are, and you can see they are not too far away from it, sometimes a factor of 10 or something, but they are there in some ways, fairly close to it. So it's a very good rule of thumb that if somebody wants to have something that is too small compared to the wavelengths, it will not be possible to build it, or you have to live with a very narrow band system. But if the system is very narrow band, you also would be suffer from a lot of losses in some ways because of this pumping field forward and back. So it means that it's hard to design things that have those properties. So if you look at an example here, a practical example, let's assume you would like to make something at 900 megahertz just to get it into numbers. And what would be that you designed it in a sphere of 2 centimeters. So very, very tiny in these cases. Then it would say here that this Q factor would be 21. So this is where we sit with these ones, which means that these ones are not really limited if we could make only antennas inside of them. They are not that small. They are fine to do it, but we cannot go much, much lower in some ways. And in many cases, of course, we need to be there. We are sitting in this very, very tiny region where we have to shrink the size of our antennas. Think, for example, about different devices you have. I mean, you have your phones. Of course, they communicate with something. Now you put something in your ear, your AirPods, for example. I mean, they are like 1 centimeter. And they are using a Bluetooth frequency. Incredibly tiny structures. So they are really the structure that you shrink a lot, Luckily, you can live with a fairly narrowband system. And most of all, you can live with a system where you are dominantly, in some ways, receiving. You're not really transmitting from. So that's easier to make for those cases. If we would like to see what the radiation pattern is, I will just show you the formulas because you have to do some calculations. But to understand that it radiates like a dipole, the only thing we have to do is to look at this radiation vector. So back where we started in the course. We now say that it is electrically small. So what sits in the exponent here is a small number. So this is a small number. If that is a small number, then you can take e raised to that one and you can make a Taylor expansion of it. And you just keep the first term. You have to make a similar expansion of the current that sits there. So you expand that in some asymptotic series that sits here that says that when it's small, it's J0, and then there's perturbation with K and so on. And if we do that and we plug it in and we do some calculations, we can actually calculate this. I will not go through it in these lectures, but what comes out in the end here is only 2 dipole terms. So those are the dominant term when you start to make it small. And that really shows that fundamentally when you start shrinking this, it has to radiate like an electric dipole, you know, the regular donut you have, and superposition of that, some magnetic dipole that sits there, which is the same shape, but basically turn 90 degrees around. And then you can combine those two in any way you like. But everything that's small radiates like that. You cannot have some directed beam coming out from. It's something very wide in every aspect in some ways. So really this donut type pattern comes out. So that is the radiation pattern that we will have. And if we have the electric dipole, yeah, then we have this radiation vector. We take the components which are perpendicular to the radial component. And doing that, we back what we did the first week, I think lecture 2, we calculated this directivity that was this 1.5 sine squared theta. So really this pattern that sits there. When you start shrinking things in electrical size, this is how it radiates. And the only thing you can do is try to modify it with a magnetic counterpart. And sometimes it can visually look a little bit different, but it's the basic radiation pattern that sits there. And the details of your antenna doesn't really matter for this. It still starts radiating like this. So when something is small, don't expect it to have a very strange radiation pattern. It has a very simple radiation pattern. And now it is, of course, when we really have gone on to electrically very small structures. When they start to go up to being like half a wavelength, then you can start change the radiation pattern. But when you shrink them, so lambda over 5, lambda over 10, this is the pattern that you start getting. And if we then would like to increase the radiation resistance, if we compare it with the dipole, we were sitting in this very low number. But we also saw that we can do the folded dipole. So instead of having a regular dipole, we folded it around here. Still, this dimension here is basically lambda over 2. So this has not been shranked anyway. It's still a big antenna. But what you did when you did that is that you increased the radiation resistance a factor of 4, because basically it radiates from one dipole there and one dipole there. And by looking at that power, you get a factor of 4. And then when we shrink our antenna, we do the same thing for a meander line. And we have one example here where we can do the same with these wires, and we just put it in a folded structure. And that is one way to push up your radiation resistance. So we don't have to suffer from a low radiation resistance. There are other ways of doing this. There's many tricks to push up the radiation resistance. So that's not something that is fundamentally giving on us as the directivity, for example. The radiation resistance we can tune between in a rather large range for these cases. If we then look at some cases of these structures, when we really shrink something, and we do it for a sphere in these cases. There is an antenna that's called a folded spherical helix. It's not maybe the most practical antenna to build, but it's a very good one and easy to understand and analyze. So think what you do here is that you take your first wire, we look at this one arm, you feed it here. So here you really feed it, plus minus, some voltage that sits there. And then you take your wire like your dipole, but you put it on a sphere and you let it go up to the North Pole and down to the South Pole. So then you have fitted your dipole within a spherical volume. And now you can do a foldering version of that, and then you just take one wire there, and you have also a short circuit that sits there. So this is the folded dipole on this sphere, turned around to shrink the size. This is a 2-arm version. You can do a 3-arm version and a 4-arm version. So all of these will have the same, basically, size. They have the same radius that sits here from the center and out. That is the same. That's still A for all of them. The radiation resistance will not really change a lot. It's almost the same because it has to do with the length of this wire. How long is this one? That's the dominant term. And in this case, they will be resonant at 0.37, Ka 0.37. So if you think that in these cases, your half wavelength dipole was 1.5. So this has shrank not really a factor of, approximately a factor of 4. It's 4 times smaller than your dipole that sits there. And if we look and see what is antenna and how they behave, we can take one example here. So this is the one with 2 arms that sits there. If we look at the input impedance here, it's inductive down here because it's short-circuited. It has some anti-resonance, and then here it has the real resonance. So that is the part that we are interested in, and that picture here is also shown there. So here you can see that the resonance is at 0.37, and now it is in the scale Ka. So that's where it's resonant. And now in these cases, it's matched to its own radiation resistance, and you can see the width of that one there. And if you do that for these cases, you will get a Q of 43 for these ones. And you got the radiation resistance here of 17 ohm. That's what you had in that one. And now it was folded 2 times. If you do the same thing and you fold it 1 more time, so now I change it. So you can see the same pattern, but slightly changed. So now there are 3 arms in these cases. So you can see 1, 2, and 3 arms down there. So that is folded 3 times. And what you can see here is that the Q is basically the same. Ka are basically the same. So the resonance is not changed. But your radiation resistance now increased from 17 to 40 in this case. So by adding 1 more in there, doing the foldering, really push up your radiation resistance, doesn't change much of the rest. I can do it 1 more time, and then we do 4 arms of these ones. And you can see the same feature again. So here we see similar things, the radiation resistance, electrical size of it, it changed a little bit. The Q went down a little bit, but not much. It just shrank a little bit. And mainly here, the radiation resistance now increased again when you went up to this. And now it's like above 50. So now you can start tuning with this, and you can actually design an antenna if you would like to, which is in some ways 50 ohms. And it has a very small electrical size. And actually, these antennas are performing according to what physics says you can do. They are optimal for its shape, very close to optimal. So they cannot in some ways be improved, but in most cases, we are not interested in a spherical shape. And here you can see all of them at once if we compare them. So you can see here, yes, the radiation resonance frequency shifts a little bit, but very, very little. And we can see that the main thing that's happening is that the slope of these lines are changing when I add more lines. That is a dominant effect. And the next thing is that the radiation resistance here is also moving up higher. Those 2 effects comes in. So that is one of those tricks that can be done or used when we shrink a size of an antenna. Foldering is really a basic, simple one that you've learned in this course, and it works for many types of antennas, not for all. And then you have to do other tricks in some ways to push it down. But it can be done in some ways. Okay, so now we can ask a question how we can really understand these small antennas in a more practical situation. And then I will come back to one thing that we start doing when we looked at arrays. And that was actually we reformulate our problem as an optimization problem. So if we think what you actually would like to do with your antenna, and let's say here that you now have a geometry where you should design your antenna. So it should be within this rectangle. So somebody has said that you have a height and you have a width here that you can use for the design of your antenna. One antenna that fits here is, for example, this meander line. You can see it has the same size here, so you can put it within this region. What will happen with this antenna is that it, of course, it radiates, it has some impedance, it has some properties. And those properties really comes from the current that sits on those antenna elements. So reformulating this problem and asking what would we like to build, we can instead ask the question of saying, I now have this geometry. What is the best currents I can just put inside of it? And what properties will that current have? And that will tell us what we would like to do with our antenna. Then we could say, can I actually find an element that fits this? And that will say in some ways how good your antenna is compared to what is the best you could really do. So if we do that, we can do it for many different cases. For example, in antennas or mobile phones, where we sit with only designed antennas in a small region, we can of course have a ground plane here. And what that means in these cases is that there you have only induced currents. You couldn't control them in these cases. So you can modify this to quite a lot of different cases. We will go through this a little bit quickly. And then in the same way, if you remember back when you did your array antenna, if you thought there, what we did is that we learned a way to synthesize radiation patterns. We learned the Dolb-Chebyshev method, binomial array, uniform array. They had some properties with side lobes and so on. But we also learned that a more general way of doing this was to rethink the problem and instead asking, what would I like my array to do? And then formulate that as an optimization problem. And if we do that with an antenna, and we say that we, for example, have a large gain, so gain divided by Q in these cases. So gain should be high because that gives a directivity. You want your Q to be low because that gives you bandwidth. Then you can say, can I maximize the quotient between gain and Q? And actually that you can do, but you can say in that case, in the physical terms, you should have low amount of stored energy and you should have a high radiation intensity. And that's actually an optimization problem you can look at. If you would like to have more directivity, you can add these as constraints. If you have embedded antennas, you can have some induced currents in these cases. So if we can formulate these in optimization problems, we can let our computer solve those optimization problems afterwards. And that will then tell us is what is the best you can do when you build your antenna. For example, if you take a size here, you have your phone, and inside of this phone here, you can put some metal and you can bend this metal a little bit everywhere. But what is the best you can do by bending it? That you can answer by these type of questions. So you can know how far you can reach. And reformulating it in the same way as we did for arrays, you will not recognize all of the details here. So that just trust me, this is something that FECO, for example, could compute by the matrices it's used to solve your antenna problem. So this underlying method of moments produce a lot of matrices, for example, this impedance matrix here, and that can be divided up into new matrices that has some physical interpretation. And then I can optimize over those ones. So in these cases, the method of moment solver just gives me a lot of these ones. And then I can take those and I can put them into an optimizer in the same way as an arrays. And I can ask, okay, what can I do? What is the best I can do for these cases? So if we do that, we can actually categorize this. And again, if we go back to what we did in arrays, we could formulate something as convex optimization problems. And the beautiful thing with these antennas is that many things here, when we look at the fields, that is, they depend linearly on the current. So if you have a current density, you double the current density, you double the electric field. So it has a linear dependence there. When you start looking at powers, it has a quadratic behavior. So the radiated power, double the current, yeah, then you take 4 times as much power. If you would like to have the size of things, that's a norm. If you take the max of things, that has a good properties too. If you do like more, Shannon, and you do capacity, actually that has also very good properties. And in these cases, these are convex quantities. And if they're convex quantities, we can do the same as in arrays. We can formulate convex optimization problems, and convex optimization problems are in some ways easy to solve. And what we did there, I will do this again rather quickly here. If a curve looks like this, it's hard to solve. But the curves that looks like this, which are these linear and quadratic terms, are simple to solve. So we don't need to know everything about these optimization techniques and how they are done. The more we know, the better there is. But the problem that is formulated like this, which pushing it back to us and say, okay, I would like the radiated power to be high. I want the stored energy to be low. And then we can write that as these optimization problems. And as soon as we've done that, we have convexity in these cases. They are solved with incredibly efficient algorithms. We cannot do it as humans. The computer can do it for us. When the solution comes, you don't get trapped in local minima, and actually your problem is solved. So the formulation is the important part of this. The computer is doing the rest for us when we would like to have something here. So if we take an example of gain over Q, if we write it down with all the formulas we have, it would be our radiation intensity here divided by all of the stored energies, and that can be written as a convex optimization problem that sits there. This is then what's called a linear form in the current I. This is a quadratic convex constraint, and this is quadratic convex constraint. Now I know you haven't studied convex optimization before, but it's a concept that is really powerful, and it applies to many, many areas, not only antennas. It's even more in like signal processing, a lot of system theory, where you realize that the algorithms you are doing are probably good, but many of them can be done better by letting the computer actually solve an optimization problem. And if we do that, we can actually get something out. So let's take an example, a fairly like practical problem that you have here. So let's say that you have a structure with a certain length, and you say this is 10 centimeters. And that is this region that we see here. So this is now 10 centimeters. And the other structure that sits here, the width of these ones is 5 centimeters. So that means it will be the size of my phone. That is as small a phone as I have, approximately at least. I don't have these huge phones. So that is the size you have. And now you say that I would like to, of course, use this phone in a certain frequency band. So let's say that I would like to go down to 600 megahertz on that size. Okay, what will be my optimal performance of an antenna if I build it in this region? And if you do that, you can see now for a quantity that in this case is gain over Q. So how much gain can you get in a certain direction divided by the Q? You will get a number here that you will not go around, which is 0.1. Which is not a terrible number if you think about Q, because the gain, okay, it's a small antenna, so think like 1.5. And then Q in this case would be 1.5 times that is equal to 0.1, which means Q would be like 15. So this would be a Q of around 15. That's it, which is not terrible. At the same time, it actually starts limited to the bandwidth that you can get out there. But what did I have to do this? To do this, it is that I have to use now this entire region here. So that is this black curve. So the blue region is what's used in your antenna design. So you actually could design your antenna in this entire space. And that's of course good. So then go to company, Apple, Samsung, Sony, or any of these and say, okay, I can make a very good antenna in these ones. That's good. But on that side, you have to put a screen, which means you're not allowed to do this case here because you're not designing an antenna. You're actually only designing an antenna that has to live in a small size next to the screen or on the sides that sits here. So if we change it and we change the perspective here, so we take instead this green here, so we take the green curve that sits there, then you design your antenna up there. So that's what you do with your antenna. And this part down here is now PEC, which is approximately the screen that sits here. It's a good conductor. In this case, it's also infinitely thin. What happens in these cases, then you're actually down here. So that means that you sit down there instead. And there you sit at, let's see, 0.02 instead. And that means that, of course, your Q in these cases will be around 100, which actually is very narrowband. So this is the challenge that you get when you really would like to design these structures where you can only utilize like a small part of the structure. You actually lose quite a lot. And as an antenna designer, you would like to utilize everything here, but in reality, you're not allowed to do it. And then, of course, you have to figure out what is the best part. Where can you actually excite these modes efficiently on the structure? Could you actually maybe get in some design space here, and maybe that could in some ways make this performance better. But when you come to this region where you sit and are, what to say, on the size of this, you're always limited in the way that it is sub wavelengths in size. You start paying a price. And you really start paying a price in the Q factor that sits there, which basically limits the bandwidth that you can get out of it. It's in some ways unavoidable for these cases. The only thing you can do to go around it is to break the relationship between this Q factor and bandwidth. And there's a lot of work nowadays in that direction. And that is really, in some ways, using what's called adaptive matching to these ones. So when you start changing your, the frequency band and the way where you hold the phone, you can adaptively rebuild your structure. And that can give you a bandwidth that you would like to have. You can let it change in some ways. And that can then increase the bandwidth for a given Q, but it will still be a lot of these reactive fields pumping forward or back around your structure. If you then do some antennas, you can of course ask, is this realistic or not? If you took these ones that I had here, you can see that it's a cross there. That is a realized antenna. So that is an antenna that is realized inside of this small little region, and you can really see that it performs according to what we can get. Simulated, of course, all of these cases. But you get very close to the real performance with designs for many of these cases. So if we look at one case here, we can ask a question here that we would like to know what is the minimum Q factor at 700 gigahertz. And we have a rectangular ground plane here of some certain size, 2.1 centimeters. And it's embedded in a PSC rectangle, which is 10 times 15. So again, it means that this LX here is 10 centimeters. And then we have a small little corner that sits up there. And if we do that, we have to see where this, what it corresponds to. So 700 megahertz, that is a wavelength of 0.43. And in this case, it's a length here that is 0.23, which means we sit here. And in that case, we basically have to jump up there. And I think we have to go around there. No, maybe I was wrong. I think we have to go to, ooh, shit, I was wrong. We have to take this one and we have to go to, I think, this line here probably. 30, yeah, this line here. And we have to go out there. So 0.23, and then we have to look at the size that sits outside. And then we can get a value out of that one, which is around 30 in these cases. So in some ways, we can actually see what is the price we pay when we only utilize a small part of some electrically small structure in some ways. What is the Q that we can get out? And in many cases, they are actually fairly realistic. So if we look at these cases and some repetition, time is running out, we can see that these small structures, they have some dipole radiation patterns. And if we would like to increase it, we have to pay a price, and that is that Q goes even higher. So bandwidth is always limited for this electrical, by the electrical size. So what is the size of your structure in terms of wavelengths? If you shrink it, you pay a price. It can be shown that this D over Q is related to, in some ways, how you can separate charge. We mentioned it once before. You can get a design which is close to 50 ohm by actually doing good efficiency and good design. And actually, the efficiency here is also in many cases shrinking for these situations. So when you make something smaller, efficiency goes down. So that is some of the understanding we can get what is the price when we start shrinking the size of our devices. And with this, we will finish this lecture. So now it's only one more week of the lecture. I think a quiz is closing tonight, I think. The 6th quiz is opening up, or it has opened up already. Then the next lecture will be about terminal antennas and base station antennas. So typical antennas that you see today and actually use today in communication systems. There are some articles here that you can take a look at. You can all download them as long as you're within Lund University. You can use these links that I have here in the lecture notes. And a little bit try to show you actually what is happening with these kind of devices. Now these are getting old, these articles. I will also show you some newer cases there. One thing is, of course, when we go to the newer one, it's harder to see them. So quite a lot of focus will be on a slightly older one where we actually see the antennas, but we will see what's coming with 5G and so on, massive MIMOs, all of these cases. We will also then talk about one modification of your patch antenna, which is called a PIFA, which is a planar inverted F antenna, which is a very popular antenna when you try to make a small device radiating close to a larger structure, which is happening in many sensors and sensor networks that are built, that there is a sensor, you need to put an antenna in it. The antenna has to be physically quite small, sitting maybe in the corner, but you can use the entire sensor to radiate. And the PIFA is a very good design for those ones. That we will also talk about next week. So with that, I thank you for today. I will stop the recording here and maybe take some questions.